We will now take a second example related to Qpsk, and in this example we will see how we will see an alternate way of defining the Qpsk signals and that will be clearer when we go through this example. So this is actually not a numerical example, so to say. It's a sort of an analysis. Suppose the four signals, the four Qpsk signals, that is, you know by this time that Qpsk has four symbols, and each symbol is represented by a signal, and these signals are distinguishable through their phase difference. So let's say that the four signals are this is one of them. The other one is cos 2 pi ft plus pi by 2, and of course Es is the symbol energy, and Ts is the duration, symbol duration. So you can see that the signals differ by a phase of pi by 2, as it was in the case of the Qpsk which we discussed earlier, but there is a small difference here which you can see for yourself, and that difference will become clearer when we draw the signal space diagram and the constellation. So this way it can be defined, the four signals can be defined this way, and you can see that the phase differ, the phase is different for the four signals and they are distinguishable by their phase difference. And of course we can write this in a compact form. We can write this in a compact form as SMT equal to, this is exactly the way we did earlier. SMT is equal to root 2 Es by Ts cos 2 pi fct plus m pi by 2. M takes on these four values, and M takes on these four values, and of course signal is in this duration of Ts, which is the symbol duration. And as we did earlier in our when we started the analysis of Qpsk, we can use the trigonometric identity and rewrite this as equal to we can rewrite like this, and of course probably before I came to this, here itself I can write this as equal to, just to copy the steps we had earlier. For M, and phi 1t is this, phi 2t is this, S1m is this, and S2m is this, including the negative sign. So that's how we expressed it earlier. A small subtle difference is there which you should have been able to make out by this time. And of course, we will recall that at the end of the last video, after solving that example, I told that here onwards we will identify this, that is the term phi1t, the basis function phi1t, as the in-phase carrier component, and we will identify this here onwards as the quadrature phase carrier component. So with the help of this, now we can with this information we can now plot the signal space diagram and show the signal constellation of QPSK, and you can see the difference between this way of representing the QPSK signals and the one which we discussed earlier. Of course, both are QPSK signals, but there is a small difference which, as I said earlier, will become clearer when we look at the signal space diagram now. So in phase quadrature, remember this used to be phi1t, this used to be phi2t. In fact, it is phi1t and phi2t, but we call them as in phase and quadrature components now. And the signal SMT is now having its coordinates. In general, the coordinates are root es cos m pi by 2 and minus root es sin m pi by 2, m pi by 2. And now we can plot. So when I take m0, I have root es cos 0, which is root es, and minus root es sin 0, which is 0. So root es 0, the in phase coordinate is root es and the quadrature coordinate is 0. So s0t will be here. S0t will be here. The I coordinate is root es. As you can see, when m is 0, you get root es, and the q coordinate is 0, because when m is 0, this becomes 0. Similarly, you can show that when m is 1, you have root es cos pi by 2, which will be 0, and minus root es sin pi by 2, which will be minus root es. So in phase coordinate is 0 for m1, and the quadrature coordinate becomes minus root es. This will be s1, and of course this will be root es. And continuing further, you can see when m is equal to 2, you have root es cos pi, which will be minus root es, and minus root es sin pi, which will be 0. So minus root es 0, minus root es 0 will be here. So this will be corresponding to s2. And of course the final one, you can see that when m is equal to 3, it is root es cos 3 pi by 2 minus root es sin 3 pi by 2, which will give you this. So again, root es, I will not write it down. So this is the constellation of the QPSK which we have discussed now. This is the signal space and the constellation. And the difference we can see that the previous one we had a constellation like this. The constellation was like this, the previous one. So I recall it is S0, S1, S2, S3. So compared to the the QPSK which we discussed earlier, here the constellation is rotated in the counterclockwise direction by pi by 4. It's rotated in the counterclockwise direction by pi by 4. So let me just confirm before it is rotated in the counterclockwise direction, or we can say that the constellation that we have discussed now, if you rotate it clockwise by pi by 4, you get the constellation which we discussed earlier, the Qpsk. But both are Qpsk signals, and of course before I proceed further, just as we did earlier, it is possible to partition the signal space diagram into regions regions which help us to take the optimum decision. So this way, this will be the decision region. This will be the decision region for the symbol S0. What we mean by that is that all the points in this region will be closer to S0 compared to the other points. Similarly, this will be the region corresponding to S1, signal S1. That means all the points here are closer to S1 compared to the other signal points. And then we have this region for S3 and this region for S2. And you know what is the significance? If you, having received the coordinates R1 and R2, or having received the projection of RT, the received random process, having received its projection on phi1t and phi2t, we just identify the point defined by those projections R1, R2, and depending on in which region that point lies, we take a decision. So if it is in this region, we say S0 T was the transmitted signal, or the corresponding symbol was transmitted. If it is here, we say S1, and so on and so forth. So that aspect doesn't change. Only thing is that the decision regions have changed. Just as the constellation got shifted, the constellation got shifted by pi by 4 in this direction, the signal partitioning has also been shifted, got rotated. That's the only difference. Performance evaluation remains the same. The symbol error rate will remain the same because no change happens in it. It remains the same. Performance remains the same. And just for sake of completion, one can show that if you take root 2es by ts cos 2 pi fct plus 2m plus 1 pi by 4. This was the signal SMT for M0123 for the Qpsk which we discussed earlier. Now if you do this here, you see that you will get the constellation which we discussed now. So you can see that this becomes cos 2 pi fct plus 2m pi by 4 plus pi by 4 minus pi by 4. So you will get cos 2 pi fct plus m pi by 2. That is the same as what we discussed just now. So that's the example. And of course, when you are mapping the die bits onto the symbols and equivalent onto the signals, you follow the gray coding, in that you do the mapping in such a way that adjacent signals are mapped with die bits which differ by only 1 bit, and diametrically opposite symbols are mapped by die bits which differ in both the bit positions. And the reason for that was explained earlier in the previous example. The reason being that these type of errors are more dominant because of their proximity compared to these type of errors. Right. And now with this understanding of Qpsk, we will move on to the next higher level modulation scheme. So remember, performance evaluation we will not do here because it's the same. The symbol rate performance will be the same as what it was for the Qpsk, because fundamentally the modulation scheme is still Qpsk. Nothing has changed. Only thing, as I said, is that there has been an additional phase shift. That's all. And that phase shift is common for all the 4 signals, which is in a way not a big difference. Okay, now we move on to the next higher level modulation scheme, which is Octal PSK. And in the Qpsk we had formed a symbol using 2 bits. We grouped 2 bits to get a symbol. We call those 2 bits as a die bit, and we grouped those 2 bits to get a die bit, and a die bit decided was mapped onto the symbol. And since you had you are grouping 2 bits, you had 2 power 2 equal to 4 symbols. Now in octal PSK, what happens is we group 3 bits, and once we group 3 bits, we have 8 symbols. So in octal, we have 8 symbols possible, and consequently, we need 8 uh, signals distinguishable by their phase difference. And these 8 signals are, as I am about to write here now. So the analysis is the discussion is similar to Qpsk, but because essentially what happens is in Qpsk you had 4 different signals which were distinguishable by their phase. Now you have 8 signals which are distinguishable by their phase. So that part, the development of the theory will be similar, but the performance analysis is slightly more complicated here because of the 8 symbols that we have. Anyhow, we are yet to reach that stage. So the 8 signals are S naught t equal to root 2 es by ts cos 2 pi f ct. S1t is cos 2 pi f ct plus pi by 4. So you can see that now the signals are going to differ by pi by 4. So 8 times you have pi by 4. You take a full circle and you come back to 2 pi. And then S2t will be the same, 2 pi f ct plus pi by 2. So increase by pi by 4. So I will not write the rest of it, and the last one will be S7t. So that will give us 8 signals, root 2 es by ts cos 2 pi f ct plus 7 pi by 4. And of course these signals are valid, or the duration of the signals is ts. And of course we can write this. So I won't write the S3, S4, S5, S6 because you know that it's going to be an increase of pi by 4 in phase. So now we will, just as we did earlier, we will express this in a compact form. SMT equal to root 2 es by ts cos 2 pi f ct plus m pi by 4 for M0, 1, 2, 3, 4, 5, 6, 7. So you can see 8 possibilities. And of course, this goes without saying. And again, repeating the steps which we followed when we discussed Qpsk, we can expand this using a trigonometric identity and write this as equal to root es cos m pi by 4 root 2 by ts cos 2 pi f ct minus root es sine m pi by 4 into root 2 by ts sine 2 pi fct, which we can write as equal to, so these things remain the same expression wise, interpretation differs, and m ranges from 0 to 7, that also differs because in Qpsk it was m0 1 2 3, so s km phi kt, and of course m0 1 2 3 4 5 6 7, and phi 1t is this, phi 2t is this, s1m is this, s2m is this, including the negative sign, and again we will call the phi 1t as the in-phase carrier component, and this becomes the quadrature carrier component, and we can draw the signal space will be two-dimensional because there are two basis functions, in phase and quadrature. Signal space will be two-dimensional, and the constellation will have 8 points because there are 8 signals here, and we can quickly draw that. We can quickly draw that. The signal space will look similar. In phase and quadrature, and SMT has its coordinates as general coordinates as root es cos m pi by 4 and minus root es sin m pi by 4, and we can start plotting the points now using these two coordinates. S0 will be root es cos 0 minus root es sin 0. That clearly says that S0t has its coordinates root es and 0. That will be this, and this will be root es. Now S1t will be root es cos pi by 4 minus root es sin pi by 4. That will be es by 2 under root and minus es by, or rather es by 2 under root with a negative sign, because when m is 1, sin pi by 4 is 1 by root 2, cos pi by 4 is 1 by root 2. So that gives us es by 2 under root, which will be roughly here, and es by 2 under root with a negative sign, that will be roughly here. So this becomes S1, and again this will be root es, because this is es by 2 under root, this is also es by 2 under root magnitude wise, so this has to be root es, simple trigonometry. And then we have for m 3. So when m is 3, so the m is 2, so s0, s1, s2 will be root es cos pi, that will be minus root es, and minus root es sin it will be root es cos pi by 2, m is equal to 2, so root es cos pi by 2 minus root es sin pi by 2. Cos pi by 2 will be 0 and sin pi by 2 is 1, so that gives us 0 and minus root es, that will be here, that will be here. In phase is 0, quadrature is minus root es, so this will be minus root es coordinate wise, this will be root es, so this corresponds to S2. And in fact, you can continue this, because now that we have seen enough of such constellations, we know that this will be S3, this will be S4, this will be S5, over here you have S6, and this will be S7. And you can see that since the distance of each of the signal points from the origin is root es, these points will lie on a circle of radius root es on the signal space. And of course that was the case with Qpsk as well, but you can see it's more pronounced here, it's more visible here that these points lie on a circle. And you can see that it's actually a combination of this and this, the constellation which we discussed first when we discussed Qpsk, and the constellation which we discussed when we discussed the second example. So it's a combination of these two, and this is how the signal space and the signal constellation for Qpsk looks like. And it is again possible, in fact one has to do that, it is possible to bifurcate this signal space into decision regions for optimum decision, and that will be like this. This region will belong to signal S7. So you see, maybe I should bring it somewhere here. Yeah, this region, rather, not the one which I told earlier, this region belongs to S7. This belongs to, so the line which bisects this arc and the line which bisects this arc, this region belongs to S7, this belongs to S0, and this will be for S1, this will be for S2, this will be for S3, S4, S5, S6, and S7 we have already seen. So this is how we can bifurcate we can divide the signal space into decision regions. So now the receiver schematics will remain the same. You obtain R1 and R2, using the same receiver schematics as the one used for Qpsk. Obtain R1 and R2, and then locate the point described by R1 and R2 in the signal space. This is how basically the decision happens, and locate that point, and if that point, in whichever region that point lies, you declare the symbol corresponding to that region as the transmitted symbol. So just as an example, if R1 and R2 such that you land in this region, you declare S70 is the transmitted signal, or the corresponding symbol was transmitted. And here as well you have to do the mapping using gray code. You have to do the mapping using gray code because adjacent symbols, the bit difference between adjacent symbols, remember these 8 symbols are found by grouping 3 bits. So bit difference between adjacent symbols have to be 1 bit at most. For example, if you are assigning 000 here, this can be 001. So the gray coding I have to follow here as well, because just as we saw in Qpsk, and we'll see that later, these type of errors will be, the probability of these type of errors will be more than the probability of these type of errors or these type of errors. In fact, the least probable will be these type of errors where symbols are mistaken for ones or signals are mistaken for one which are lying diametrically opposite to them. These will be the least probable events, whereas symbols being detected as or signals being detected as the ones lying very close to them, adjacent to them, will be the dominant, and the probability of these will be in between. So the performance evaluation we will carry out now. So having understood the Octal PSK, what actually Octal PSK is, we will now carry out the performance evaluation. To evaluate the performance, we will adopt the same method which we adopted for evaluating the performance of Qpsk. In that, what we will do is we will find out the probability of a symbol being detected correctly and we will subtract that from 1 to get the probability of the symbol, the probability that the receiver makes an error in detecting that symbol. And due to the same reasons, the probability of error in any of the other 7 symbols will also be the same. For the same reasons, in the sense the symbols are equiprobable, and due to the symmetry in the signal space diagram, the constellation as well as the noise which corrupts the symbols being additive white Gaussian and additive white Gaussian noise. Okay, now if say let's begin again. Let's just go to the constellation, the signal space, the in-phase quadrature, and we have this point corresponding to the signal S naught t, and S1 t is here. 1, 2, 3, 4, 5, 6, 7. S7 is here. S7t is here, and the bifurcation of the region, the division of the signal space into decision regions was shown a short while ago. Now we just concentrate on the symbol S0 or the signal S0t, and we observe that the bifurcation or the division is in this way, in the sense whenever the point described by R1 and R2, that is whenever the point described by R1, R2 lie in this region, it is declared that the signal is S0 t, or the symbol is the one corresponding to the signal S0 t. So what we do now is we will find out the probability that the point described by R1, R2 lies indeed in this region, when S0 t is the transmitted symbol. So for that, we have to have with us first the conditional density. In fact, we have the conditional density functions of R1 and R2. In fact, we can write them down. We note that density function of R1 given signal S0 is 1 by root pi n0 e power minus R1 minus root es whole square by n0, because when transmitted signal is S0 t, we receive the received random variable will be root es plus n1, and n1 is 0 mean Gaussian with variance n0 by 2. Similarly, when S0 is the transmitted signal, R2 would be because when S0 is the transmitted symbol, R2 would be just the noise. Now, with the help of these density functions, it's indeed possible to find out what is the probability that R1 and R2, the point described by R1 and R2, lie in this region. But we can simplify the derivation or the analysis if we operate on the polar coordinates. So what we have is IQ is actually a Cartesian coordinate. We have the signal space in the Cartesian coordinate system. We are represented this in the Cartesian coordinate system. But due to the fact that the division of the signal space, the bifurcation of the signal space into various decision regions has a circular symmetry, we will be better off using the polar coordinates. We will be better off using the polar coordinates, wherein we will define rho as equal to square root of r1 square plus r2 square. So if, say, for example, r1 r2 defines, let's say r1 r2 corresponds to, let's say r1 r2 corresponds to some point like this, let's see, some point here. That means r1 is this, r2 is this. Let's say this is what the point is. Now when we convert this to polar, rho will be the distance of the point from the origin, as you know. So rho will be this, and phi will be tan inverse r2 by r1, where phi will be the angle made by this with respect to the in phase axis. This angle will be phi, and this will be rho. So you know this polar coordinate system. Now since this angle is pi by 4 and this is also pi by 4, we observe that this is pi by 8 and this is also pi by 8. So having transmitted the signal S0t, we will receive it correctly, we will detect it correctly, provided phi is between minus pi by 8. So this is 0, minus pi by 8, pi by 8. Phi is between minus pi by 8 to pi by 8. So if phi lies between minus pi by 8, if phi lies between minus pi by 8 to pi by 8, when S0 is transmitted, then that signal will be S0 will be detected correctly, because whenever phi is between minus pi by 8 and pi by 8, the point described by R1 R2 is always in the region corresponding to the signal S0, or in the region which is specifically reserved for the signal S0. In that, whenever you are in this region, you declare the transmitted signal as S0. So this is the condition. If this condition is satisfied, we have received S0 correctly. So we observe that, we note here that Phi is actually a function of two random variables. Remember, R1 as well as R2 are random variables. And when S naught t is the transmitted signal, as we have assumed, when S naught t is the transmitted signal, R1 is having a mean root es and variance n naught by 2, it is Gaussian, and R2 is having a mean 0 and variance n naught by 2. Now that means phi will also be a random variable. Its distribution will not be Gaussian because it is a function of a ratio of two Gaussian distributed random variables. It will have some distribution. If we could find out what is the distribution of phi, it's possible to find out the probability of phi lying between minus pi by 8 and pi by 8, and that gives us the probability that S naught t is transmitted or received, or S naught t is detected correctly. So we should have the density function of phi given that the transmitted signal is S naught t, and that can be derived. I have the derivation, it is there in the appendix or annexure of the study material which I have uploaded. I will not do it here, it's a bit lengthy, but I will give you the result straight away. The density function of phi, which is defined as tan inverse R2 by R1, will be, and I think I can remove this also, because we know when our phi is between minus pi by 8 and pi by 8, when S naught t is the transmitted symbol, it means that we are detecting S naught t correctly. So density function of phi given S naught is the transmitted signal will be, so I am not deriving it here, you can find the derivation in the annexure of the study material. Probably, if possible, I will make a video of that and upload, and if possible I will give a link of that in the description. If not now, maybe in future, sometime in future. So the density function of phi is, density function of phi given that S naught is a transmitted signal will be cos phi into e power minus es by n naught sine square phi minus es by n naught sine square phi into, so this term into 1 minus q root 2 es by n naught cos phi. So this is a fairly long expression. You don't have to memorize this. If there is a question asked on this, I will give you the expression, I will give you the density function. You don't have to memorize this. If there is ever a question where you have to use this, then I will give this expression. So you should be knowing how to use this, that's all that you should be knowing. You don't have to memorize the expression. And what we have to now find out to know whether S naught t is detected correctly, that is, the probability of S naught t being detected correctly will be the integration of this density function from minus pi by 8 to pi by 8, because whenever phi is between minus pi by 8 and pi by 8, given that S0 is the transmitted symbol, we will detect S0 correctly. However, the problem here is that this integral, when you substitute this over here, it cannot be, one has to use numerical methods to evaluate it. So what we do is we'll simplify this. We'll go for an approximation, and the approximation will be valid. The approximation will become better and better as ES by N0 becomes larger and larger, and in any practically useful system, ES by N0 will be reasonably large. So this approximation which we are about to use now will be valid in most of the practical situations. So this is the integration that we have to perform, and because of the fairly complicated nature of this density function, rather formidable expression, so we will simplify it. And the simplification that we are going to use is, we will approximate, I had discussed the approximation of Q function in one of the earlier lectures. So this, in fact, I had shown you how we arrive at this approximation. This can be approximated as equal to e raised to minus Es by N0, that is exponential, minus Es by N0 cos square phi divided by 2 root pi root Es by N0 cos phi. So we can approximate it like this, and this approximation of Q you substitute over here. You substitute this approximation over here, and I will not show all the steps. Certain terms are going to get cancelled. I will just explain it. I will give the outline how it happens. You substitute for, it's an approximation, remember, you substitute for this Q, for this Q you substitute this, and we straight away see that when you expand this bracket, this into 1 will remain as this itself, and in place of Q we have this, and this into this, if you see, cos phi will get cancelled because this comes in the numerator, denominator here. You have cos phi in the numerator, so cos phi will get cancelled. Root Es by N0 will get cancelled. Root pi and root pi will multiply with each other, and that will give us pi, and 2 will be there as it is. The exponents, we are multiplying these two. The exponents, cos square plus sin square, will give us 1. So the result will be e raised to minus Es by N0. So what happens is, when we substitute this, due to the reasons I explained just now, I will not work it out. I just have to simply write it down and cancel it off. It's something that we can do. We get P phi given S0. Given S0 means, given that the transmitted signal S0 is approximately equal to, remember it's an approximation because Q is approximated like this, which is valid for large values of Es by N0, 1 by 2 pi e power minus Es by N0 plus root Es by pi N0 cos phi e power minus Es by N0 sin square phi, that is this into this, minus, now effectively we are multiplying this with this, and we get 1 by 2 pi e power minus Es by N0, and this clearly tells that these two will cancel each other. which means that the density function of phi given S naught is approximately equal to this. Density function of phi given S naught is approximately equal to this. And now the probability of correct reception of, or rather the probability of detecting the signal S naught t correctly becomes an integral from minus pi by 8 to pi by 8 of this, because this is now approximated to this, and root es by pi n naught can come out of the integration because there is no phi in it. Cos phi e power minus es by n naught sin square phi d phi. And we can write this as equal, you see this function is actually an even function of phi, it's an even function of phi, so we can write this as equal to, since it's an even function of phi, we can write it as equal to 0 to pi by 8 2 times, because it's an even function. So 0 to pi by 8 2 times. Now let root es by n naught sin phi be equal to, say, u. We'll make a substitution. This means that cos phi d phi is equal to root n naught by es du. So in place of cos phi d phi, you substitute this, that is, we are just changing the variables. When we make this substitution, this becomes 2 times 1 by root pi. We'll substitute the limits now in a short while. Cos phi d phi has become this root n naught by es, and this I have already cancelled. You will have e power minus u square du, and the limits will be 0. So when phi is 0, u becomes 0 because sine 0 is 0. When phi is pi by 8, u becomes square root of es by n naught sine pi by 8. If we evaluate this, we'll get the probability of the symbol being detected, S naught t being detected correctly. And we notice that the term which is getting integrated, the function which is going integrated, leaving out this 2, the function which is getting integrated is this, and this is actually a Gaussian distribution, the density function of a random variable which has mean 0 and variance 1 by 2. This is actually a Gaussian distribution which has mean 0 and variance 1 by 2, and it is integrated from 0 to some particular value. So that will look like this. This is the function which is getting integrated. It is integrated from 0 to, say, some value which is nothing but root es by n naught sine pi by 8. Sine pi by 8 will be positive. So it is going to be something like this, and this is the area which we are concerned with. Of course, twice this area, because the 2 I have left out. This is the area which we are concerned with, and this area will be the same as half minus this area, because one side of the density function, if you integrate, or a Gaussian density function, if you integrate, zero mean Gaussian distribution, if you integrate from 0 to infinity, you will get 1 by 2. And what we are interested in is in this area. So 1 by 2 minus this will give us this. So we can rewrite this as equal to 2 into 1 by 2 minus 1 by root pi root es by n naught to infinity e raised to minus u square du. And you can again go for a second substitution. Probably this second substitution could have been incorporated in the first substitution, but I didn't do it. You can go for a second substitution, say u is equal to v by root 2. You can make this substitution, and it is possible to, once you make this substitution, it is possible to express this as a q function. I will not do it. It's left as an assignment for you, small exercise for you. Make this substitution here, and you will be able to write this in terms of the q function, and the result will be, that is, if you make this substitution and express the integration in terms of q function, you will end up getting this as equal to 1 minus, the 1 arises because when I open up the bracket, 2 and 2 gets cancelled, 1 minus 2 times q. So this q is what you will get if you make this substitution here, 2 times q root 2 es by n naught sine pi by 8. And hence, now this is the probability of the signal S0t being detected correctly. 1 minus this will give you the probability of S0t not being detected correctly. That means the receiver making an error in detecting S0t. So error in detecting signal S0t will be S. So this is the probability of error in S0t is equal to this. Now, if you calculate the probability of error in detecting S1t, you should get the same result because of the symmetry. If you calculate the probability of error in making the receiver making an error in detecting any of the other signals, the 7 signals, be it S1, S2, S3 up to S7, you will see that it's the same as this, which means that the probability of the receiver making an error in detecting a symbol, the average probability of error will be the same as this. So this is the probability of symbol error for OPSK or Octal PSK. Even sometimes it is called as 8 PSK. You can compare this with the remember, this is an approximation, because you know at some point we have approximated we have in fact proceeded with an approximation of the density function of phi. So this is an approximation, and you can compare this with the approximate symbol error rate of Qpsk, approximate symbol error rate of Qpsk, which, if I recall correctly, was, I'm not able to locate it and I'm not able to recall it from my memory. It was, yes, I think it was approximately 2 times q root es by n naught. Please check this. So you can compare it, and in the study material which I have uploaded, you will find the plot of these two, and you can see the relative performance of symbol error rate, definitely the symbol error rate here will be more than the symbol error rate here. It will be more here, and the reason being quite obvious from the signal space itself. The reason is quite obvious from the constellation. So this is the constellation for Qpsk. The distance is root 2 es. The distance is root 2 es, whereas the constellation of OPSK or Octal PSK is this. The Octal PSK constellation is this, and the distance between edges and symbols using simple trigonometry, because we know this is root es, this is also root es, and we know this is pi by 4. So you can use elementary trigonometry. This is not a right angle triangle, by the way, but if you draw a line which bisects this angle to pi by 8 and pi by 8, you will get a right angled triangle, and you can use simple trigonometry and show that. Again, I'm leaving it as because it's very elementary. You can use simple trigonometry and show that this distance, that is distance between adjacent signals, or distance between the adjacent signals which represent the symbols, of course, is equal to root 2 minus root 2. So 2 minus root 2 under root es. You please show this. You can derive this. It's a simple thing, simple trigonometry, you'll get the result. So this, we call this as the minimum distance. In fact, the distance between the shortest distance that you have, adjacent symbols, we call that as the minimum distance. And as I discussed earlier, that type of errors where a symbol is getting detected as the one very adjacent to it will be dominating, because from the signal space we know that this is the shortest distance. So crossing over from this to this is more probable than crossing over from this to some other decision region. So this is why we have the Octal PSK or 8 PSK performance inferior compared to the Qpsk for the same signal energy es. Root es is the radius. Root es is the radius here also. So that completes. So please take a look at the plot where we show the symbol error rate of Qpsk as well as Octal PSK, and also please derive this. So in that plot you can see how these two, the symbol error rate performance or the probability of error, probability of symbol error fares between these two, how comparatively they look, comparatively how they look. So that's task for you.